Hi, welcome back to Petroleum Downstream Crash Course 7. Today I want to talk about the Atmospheric Distillation Tower. Now, previous video, we see that after our crude oil was treated by desalting, we removed our salts and metals, some of the metals and some of the other impurities. Now we are ready for distillation. So we have desalted crude. Let's say at about 120 Cs. Right, so what do you need to do next? Probably we want to send it to some heater. And as we all know, we all see this big column, as famously shown in many videos, what this distillation tower would look like. Something like that. But how do we arrive at the design of an atmospheric tower or atmospheric distillation column? So, what do we remember about distillation before? We have ASTM D2892. This is a standard distillation test with 15 plates and reflux ratio of 5. So, what happens during there? They have a flask plus a column where you have plates in there, 15 plates. I'm not going to draw them all out. Then you have a condenser on top plus a reflux. This is a reflux, this is distillate. So R by D equals to 5. So this is batch distillation, where you have a batch of oil, you heat it up, and you distill it. Now, is this practical for a real distillation column, where you have 150,000 to 250,000 barrels per day, or barrels per stream day? They are about the same thing, for now. I can explain more later. Barrels per stream day of crude. So are you gonna like have a mega flask and put like a few barrels in, distill it, and then wait for it, and then you keep doing this process over and over again? It's not very economical. So if you have so much crude to distill, you might as well feed everything in here. And you do it continuously rather than doing one batch at a time. So we have a bottoms, we have a feed, and we have some heat. This is our bottoms product, which is the sticky stuff, the very heavy boiling point stuff. Now, from here, we see that we want a continuous process. So it's desalted crude at 120 Cs. We have a heater, and we know we need some kind of pump to pump it into our, what do you call that, atmospheric distillation column. So it doesn't exactly operate at atmospheric pressure, but slightly higher, because you need the pump to pump the liquid in so that the liquids can actually flow. So maybe we are looking at 0.5 to 2 bar gauge, about just slightly higher, maybe 2 to 3 atmospheres of pressure. So, are we just going to have the tops and the bottoms? Are we just going to have 2 streams drawn off? Also, not very good, because then you'll need a lot of distillation columns at the back excuse me, to separate out your naphtha, your kerosene and gas oil, and everything else. So people, instead of doing this, they'll do something like this. Alright, so you have a heater, and we'll have a column here. So they're going to draw out some side streams. They call it side streams. And this is the bottoms. Alright, there's no problem there. And you can see we don't need the heater at the bottom of the tower because we have the heater here already. So it does the same thing. You just put it in the tower and let the light stuff go up, the heavy stuff go to the bottom. So what kind of fractions do we have here? We have butanes and lighter at 30 degrees and below. We have light straight run gasoline or naphtha at 30 to 90 Cs. Excuse me. We have heavier naphtha. Okay, this is known as tops also. The light strain run naphtha is known as tops, just for your information. But heavy naphtha, which is the heavier part of gasoline, excuse me there, 90 to 200 Cs. Sometimes it's 180, sometimes it's 200. So it depends on the kind of boiling point range you want. But 200 C is very easy to remember than 180. It's much easier to remember. Next cut, you have kerosene, 200 to 270 Cs. And you have light gas oil. Here it is 270 to 320 Cs. Heavy gas oil, 320 to 420 Cs, roughly. And yeah, let's check again. Yes, this is our table from Penn State. It's about 420, yeah? So 320 to 420, heavy gas oil. Sometimes it's also called atmospheric gas oil. Excuse me. Atmospheric gas oil, AGO. And next, we have our long residue. It's 420 plus plus plus. Okay? So this is our bottoms. Because its boiling point is so high, it will be drawn off at the bottoms. And hopefully you have butanes, light straight runs, heavy naphtha, kero, light gas oil, heavy gas oil, all from here. Let's draw a column again with the pump. So it's 2 atmosphere, something like that. And this is the heater. So we have refinery gas, light straight run, heavy naphtha. Okay, let's draw a bigger column. And remember, crude is usually heavy, so most of it is very heavy stuff. Like you've seen the essays before, like 50% of that stuff is going to be long residue. So it makes sense to put it near the bottom rather than you put it at the top, then there's a lot of remixing that occurs. Anyway, so heavy naphtha, kero, somewhere here, light gas oil, heavy gas oil, long residue. Okay, so now we need some reflux to the tower to perform controlled cooling. And we also know that if you actually draw these fractions off, it will not be very pure, heavy gas oils or kerosenes or something like that. There'll be still lots of light stuff in there because you have to go up the plates, and this will not be 15 plates. This is not 15 plates because it's the separation. You need it to be very good. So we're talking about separations here. We need very good separation. So you can't use 15 plates. It's too poor. The ideal of 100 plates, well, that may be okay, but still, the more plates you have, the longer tower you will need to construct. And that's going to be very expensive. So not a good idea. Somewhere in the middle, maybe 40 to 60 trays will be good. So this is about 40 to 60 trays. Oh, yeah. And so you have 40 to 60 trays, and we have decent separation. But you see, the thing here is that there's still going to be some light components inside each of these side streams. And too much draw off, also too many side streams, is going to result in a very big cost if you want to design one big tower that does everything like that. So let's tackle the problems one at a time. So when you have, let's say, a diesel, or light gas oil, you're going to have some of the more volatile stuff. More volatile stuff that comes from this fraction. And what are you going to do about it? You can either construct another distillation column, and that's going to be expensive. Is there a cheaper option? Yes, there's a cheaper option. It's called stripping. Now, what is stripping? Stripping is just like evaporation but done professionally. So imagine yourself on a hot day, the sun is shining, and you're sweating. You're perspiring. You're sweating a lot, and it's a very humid day. In a humid day, you'll feel much excuse me, you'll feel much hotter. You feel much hotter because your sweat can't really evaporate, because there's so much water vapor in the air already. If there's so much water vapor in the air, you can't evaporate as much, and you're going to sweat more, and you're not going to have as much evaporation. So what do you need to do? You need to have a fan, hopefully blowing dry air at you. If the dry air is going to be very dry and cooling, it will cause water to evaporate, and you have hot humid air blowing away from you, hot humid air, and you feel a lot cooler. So what happens is that a lot of the water vapor from your body, or the water from your body, becomes water vapor, and then the dry air carries it away with the hot humid air. So that's why you feel cool. So if the air has less water vapor, it's more effective in getting your sweat to evaporate. So the same thing with strippers. Let's say you have light gas oil here, plus some, let's say light straight run gasoline, which you want to get rid of. So what you have, hopefully, when you come out, is just light gas oil, which is again 270 to 320. What do you do? What can you pump inside? Are you going to do air? Are you going to get air to get this light straight run gasoline to evaporate? Because light straight run gasoline, or any other kind of distillate, is going to behave like water. When you throw in a kind of gas at it, then it becomes less humid, in the sense that less light straight run gas. Alright, let's have a bottle here, a mixture of LGO, light gas oil, and light straight run gasoline. If you're going to blow air, and this light gas oil, this light straight run gasoline is like the water, you're going to blow air in there, and this light straight run gasoline is going to evaporate. But if this thing is so saturated in light straight run gasoline, you can't evaporate much anymore. So you need some kind of diluting gas or air to get it out. So you blow air inside, dry air, so-called dry because it lacks light straight run gasoline. So blows in and comes out, light straight run gasoline plus air. This is a vapor. Is that a good idea? Not really, right? So air is definitely out of the question, because air plus hydrocarbon vapor equals boom. Not good, not good. Safer alternative and very practical. Use water. or steam. In refinery, they call this stripping steam. So stripping steam will again be like the air, except now that you're not trying to evaporate water vapor, you're trying to evaporate all the light straight run gasoline and everything else out from your light gas oil. Well, it's a safer system. Alright, so what comes out, you have steam plus LSR, like straight run gasoline, not naphtha. And here you have about 4 to 8 trays. So this is what stripping does. Stripping gets the lighter stuff out of the mixture, and this is what you're left with. It's going to be much better, and the boiling range is going to be much more restricted. Now let's put this into our tower. I'm not going to draw the whole preheating and the heating and the pump again. So let's just draw this arrow to represent heated crude. Alright, so we have light straight run, we have butanes and lighter or gas, we have Caro, light gas oil, heavy gas oil, long residue. So light straight runs, we want to evaporate this, the butanes and lighter. So we have a side stripper. So we have steam here, or low pressure steam, they call it LPS. So light straight runs plus other stuff. So the stripping will help to get rid of the butanes and lighter stuff and pumping back as the gas form into the tower. Alright, so this is light straight run, this top stream, light straight run, or rather butane plus steam. Butanes and lighter plus steam. So the top column is going to have steam. Alright. Now is this practical though? Light straight run gasoline is 30 to 90. This steam is going to be more than 100. Practical? Not really. Steam is going to just evaporate all the light straight run gasoline, everything out. So you can't have this with light straight run gasoline. She here should have heavy naphtha. Yeah, you can't have light straight run gasoline being stripped by steam because it will just evaporate everything. So, best you can do is to get light straight run and lighter on top. They just call it tops. This is the distillate that comes out from the top. Heavy naphtha. I just call it HN. So to evaporate off everything, you'll get steam. So going back into the tower, this is steam plus light straight run and lighter. I just put etc. here to represent that. Light straight run and lighter. So heavy naphtha 90 to 200 Cs. Alright. Side stripper 1 to 8 trays. Wait, no. 4 to 8 trays. Alright. Next, so you need your kerosene cup. Again, strip it with steam. It's Caro. Okay, let's draw a longer tower because we know we're gonna have a lot of fractions. What else? Light gas oil. steam, and back. This Carol is 200 to 270. Light gas oil, 270 to 320. And you have heavy or atmospheric gas oil. Okay, and even here, excuse me, even here you can have another side stripper, except they just make another section at the bottom. Steam will go here, long residue will go here. This is called long residue, which is the bottoms of the atmospheric tower. And yeah, bottoms of the atmospheric tower, they also call it atmospheric reduced crude. Excuse me. Yeah. Right. So you can see we have a lot of steam streams going up into this tower. And we have steam, a lot of steam, coming up into the tops of the distillation tower. And we have lighter stuff as well. Next, what do you do with the top to purify it? One way we can do is to cool it down with cooling water into a separator. Separator will have one layer of oil on top, or one layer of light straight run gasoline on top, another bit of water, because the steam will condense. And this we can draw off as light straight run, 30 to 90 Cs. This we can send back as reflux. Light straight runs or light naphtha. So, yeah, pretty good, right? That's what our crude tower will start looking like. Yeah, something that resembles a real crude tower now. Okay. Next problem. How hot do we heat the crude? So how hot do we heat the crude? Well, we notice that if we heat the crude too much, or oils in general too much, we notice that they start to char. They form like carbon residue, right? Carbon residue. If you see in deep fryers or something of that sort, or even hotter, you see lots of carbon residue. This is known as coke, which is just a substance really heavy in carbon. And we see lots of smoke, stuff like that, right? So this process will degrade the oil, and this is known as coking. Coking or cracking. So cracking is basically like if you decompose the oil under heat, what will happen? And if cracking, the extreme version of using cracking for oil to undergo cracking under heat is called coking. I mean, there are other forms of cracking which will happen as well. They might be useful if it can be controlled. But the extreme form of cracking is known as coking. Alright? So, we don't want this to happen. This cracking or all this to happen in our distillation tower. The safety barrier, a rule of thumb, very easy to remember rule of thumb, is that at 400 degrees, cracking will start happening. And if cracking starts to happen, then your crude tower is kind of messed up. So what do? We can have a safety barrier. Maybe about 10% down. we get about 370 degrees C. Okay, 370 degrees, that's our max temperature of the crude. Because if we operate at 400 or even 399, there'll be some fluctuations, and once it hits over 400, oh, that's it. Some bad things gonna happen. Okay, the whole tower will start clogging up and you have less output, less distillation efficiency, stuff like that. So 370 degrees is what we want to go with. Now, if we heat the crude to 370 degrees C, we notice that our atmospheric gas oil will not be separated as well. Because atmospheric gas oil will be 320 to 420 degrees C. So we cannot heat up too much of this atmospheric gas oil. Maybe we have 370 degrees C because of that safety barrier. So some of this heavy gas oil, if you want to have this safety barrier, will go into the bottoms of the crude. So let's redraw everything again. Excuse me. Let's redraw everything. So we heat it to 370 degrees C. Just call it tops plus butane, lighter. Condense these guys. So I'm gonna draw everything out again. So that this is water, and there'll be some gas coming out. There'll be a gas layer, an oil layer, and a water layer. All right. So the side strippers here again. So the residual will be at 370 degrees. So instead of drawing heavy gas oil from our atmospheric tower, we can draw maybe light gas oil plus kerosene plus light straight run gasoline. So this will need to separate even more. And if we want to have our safety barrier, we have a heater and pump again to ensure it is at 370. If we want to make sure we have a safety barrier, we can operate another tower, maybe at a reduced pressure, to draw off our atmospheric gas oil and heavy gas oil. Here we have our long residue. Now this is the version with safety version, right? Now, the last problem we want to tackle is our reflux. So do we want multiple sources of reflux or single? That means everything comes out at the top. Single reflux means if I look at our tower, the only reflux I have is from this light straight run gasoline. Everything is going to pour back here, and that is supposed to cascade down and cause the cooling. So would I rather have that, or some of this heavy naphtha, I put it back here, Caro I put back here, and light gas oil I put back here, something like that. Do I want multiple streams of reflux or single? Multiple or single? Well, with a single one, we have less control. We have less control because we only have one reflux ratio to play with to control the tower. So if I adjust the reflux here, then every stream will be affected. The purity will be affected. So if I want to have fine control over every section of the tower so I can manipulate one at a time, I can have a reflux here. Instead. Okay? That's a multiple reflux. So if I control this reflux ratio from the kerosene portion. I can control the amount of purity in my light gas oil, heavy atmospheric gas oil, or heavy gas oil, and I won't affect anything over here as much as compared to when I just control this light straight run and everything down will be affected. So this gives you more control over the tower. Multiple reflux gives you more control. I suppose, yeah, there's a lot more reflux ratios you can play with. And secondly, you notice that this carol will be at 200 degrees when it just cools. And this reflux rate is at 30 degrees. Roughly 30, 40, 50, something like that. And this heavy naphtha will be at 90 or less. This will be at 270 or less. So if I use this to reflux back into the tower, what will I get? I won't need to cool as much naphtha to 30 degrees from 90 degrees. Instead, I can just cool down my heavy naphtha to 90 degrees from the, or even less, maybe I can do from 90 to 70. I can send it back into the tower, and I don't need to use cooling water. I can actually use crude. My incoming crude will be at 30 degrees C. 30 degrees C crude can cool down this heavy naphtha so that I don't need to use cooling water. I can cool down this heavy naphtha, I can send back. It will come out at about 150 or 140. I can send it to my desalter. Desalter, right? Yeah, desalter. So at about 150 degrees. And after it reaches about 150 degrees, it comes out at 120 degrees. Maybe because of some cooling. That's just an estimate. I'm not sure of the actual numbers. There's some cooling. So 120 degrees. 120 degrees. I can use more heavy naphtha to heat it up, or I can use the carol. So I can pump my crude here, cool the kerosene down a bit, send it back. And then crude oil will reach about 200, maybe 180, 170. If I heat it some more, I can use this light gas oil fraction, use the crude oil to cool it down, and my crude oil will heat up in a heat exchanger, send it back into the tower, and now there you go. You have multiple reflux, less cooling water. I can use less cooling water. If you're a chemical engineer, you know this is very good, because multiple reflux means more heat integration. More heat integration means less utilities used, so less costly. So of course you want to use multiple reflux rather than single reflux. So in conclusion, our atmospheric tower will look something like this. After coming out from the desalter, I'll have a pump. I'll have something known as a preheat train, where my crude oil actually goes through a heat exchange with each of these fractions to heat it up, and the remaining bit, you just burn some gas or burn something in a furnace to heat it up to about 370. If you want to be safe, 370 crude goes into the atmospheric tower of 40 to 60 trays. 40 to 60 trays, and then this can be separated into the various fractions. So we use steam to strip out all the light components to the top, and at the tops you will collect your tops light straight run naphtha and butanes and lighter and light straight run naphtha or gasoline will be condensed here in a separator. This will have a gas layer, vapor, and butanes and lighter. Light straight run, you can send back to the tower as reflux. Water, you collect it out. And next, you have side strippers for heavy naphtha. You draw a heavy naphtha fraction. Side strips, about 4 to 8 trays. You have steam going in. And the heavy naphtha will come out hot. It will heat up the crude. And you can send some of it back as reflux. Kerosene, 200 to 270 Cs. Again, same side stripper, similar side stripper configuration. You have stripping steam to get all the light stuff out, the heavy naphthas and the light straight runs and everything else. So it'll come out at about 200. You can use it to heat up the crude and again send back to reflux. Same thing for light gas oil, just that is 270 to 320. And heavy atmospheric gas oil, which is 320 to 420. Now, if you want to draw out, do a safety kind of thing, you can actually draw it out at 150 to 150 mmHg, which is, what do you call that? It is near vacuum, low pressure. So you have some packings in this tower. Again, you have steam. Now you have steam in the vacuum tower. Alright. And the long residue will come out here if you want to maintain that safety barrier. Okay, that's all I have for you. You just explored the design of the atmospheric distillation tower. Hope you enjoy your day. There's no homework for you today. Alright, see ya.